Hey everybody, here's the notes from today's class. So we want to make sure that we know this is distance learning week 6. We started these in class, but I know I was having technical problems in period 3 today. So we'll just do a video for them. All right, so a little game for you. I want you to take a look at these terms in each of these sequences. And we're going to learn that a sequence is just a list of numbers, and they can be any kind of number. We have positives, negatives, or items if we want to. And what we want to do is we are math thinkers. So because we're math thinkers, we always want to wonder, is there a pattern that we can find in these numbers? So pause the video and see if you can identify the patterns in numbers 1 through 4. All right, so if you look at that first one, those are your friendly numbers. I hope you recognize your cubes. 0 cubed, 1 cubed, 2 cubed, 3 cubed. So we just continued on with 4, 5, and 6 cubed. Number 2 is a girl-boy pattern, but also ABC. So in addition to naming or coming up with some, this is an Aaron, coming up with some girls' and boys' names, you want to be going up the letters of the alphabet. Now the interesting thing is we're going to talk about sequences that are infinite, and you wonder, could this one go on forever and ever? I don't know. Take a look at number 3, and you can see I've divided by 2, and we have that conversation. Could this go on forever and ever? Sure, because these numbers are just going to get closer and closer and closer and closer to 0. We can even talk about 0 being that asymptote my numbers are going to get closer to, but never ever cross, that's for sure. When we look at number 4, we can see that each of these things, if we multiplied it by -2, and we multiply the previous one by -2, so -2 times 1 is +2, and then -4, +8, and so on. And this one for sure can go on to infinity. All right, now that you've got the hang of it, go ahead and check out 5, 6, and 7. All right, how'd you do? So number 5 is a little tricky, but if you unsimplify the fractions and put everything in a common denominator, you can quickly see it's 1, 2, 3, 4, 5, 6, 7, 8 tenths. So could that go on for infinity? You bet. And we added our infinities to our other patterns too. So check out this one. It's a little bit different because instead of having the same thing happening over again, like adding 1/10 or multiplying by -2 or dividing by 2, we're adding something different each time. So we're adding 1, then adding 2, then adding 3, then adding 4. So is this a pattern I can continue? Sure, absolutely. And will it go on for infinity? Yes, absolutely. But we're going to talk about whether or not this is a pattern that fits what we're looking for in today's objective with today's lesson, because this isn't a common difference. That's going to make things a little bit trickier for us. This last pattern, the 26th letter of the alphabet is Z. The first letter is A, the 25th is Y, the second is B, the 24th is X, and eventually we'll run out of letters of the alphabet. So this is what we might call a finite pattern where it's not going to continue on forever and ever. All right, let's get down and dirty with these notes. All right, so here's what we talked about in class. We're going to start talking about these arithmetic sequences. We're going to write them as functions. And remember, anytime that we write something as a function, that's kind of that f of x idea, where we can determine some kind of rule. If we determine the nth term, that is going to be whatever place value we have, wherever that n is in our order of our sequence. So again, we'll talk about the sequence, a function whose domain is a list of natural numbers. And we'll talk about why this is an important thing in just a little bit. If your domain is not specified, you're just going to understand that your lists start with 1. And here's the thing that I want you to think about. When we put a sequence or a list of numbers in the idea of a function, I want you to imagine that XY ordered pair chart. And instead of an X, let's go ahead and talk about N. So what N represents is our domain, our input, for each numbered term that we have. So our input is actually the number of the term that we have, not necessarily a specific value. That is why we can only have our real numbers. We have a first term, a second term, a third term, a fourth term, and on up. So each of these n values represents the position of each term in the sequence. Now the range, or our output, is going to be that value that is in the sequence, the specific terms of the sequence. So when we do these, you can kind of see what we're talking about in just a little bit. All right, first of all, here's another number pattern for you. It's similar to the one that we had in our warm-up, where you can see each time I'm adding 1/3. So 1/3 plus that 1/3 is 2/3. 2/3 plus another third is 3/3. Of course, that's 1, and so on and so on. So if somebody asks me what the next 3 terms are, my 6/3 and my 7/3 and my 8/3 are going to continue that pattern of adding 1/3 each time I go. Now, if you can simplify, remember you always do. So when we talk about what is the third term of this sequence, what we're talking about is here n is equal to 1, here n is equal to 2, and here n is equal to 3. So 1 is going to be our third term. So if this is our third term, fourth term, fifth term, sixth term is going to be a 2. So when we're wondering, is it a finite or an infinite sequence, we're going to take a look at these 3 dots, and we're going to know that it is an infinite sequence because it can go on forever and ever with that pattern of adding 1/3. So we're going to define and talk about these sequences in the terms of 2 different rules. A recursive rule is coming soon, so we're going to talk about that in a couple weeks. But our explicit rule is what we're talking about today. And what we want to understand is we want to come up with a way of writing a formula that defines that term based on its place in the sequence. And that place in its sequence is, by the way, our n value. So when we talk about an explicit rule, we're going to turn each of these patterns into an equation that we can use. So here's an example of an equation that we can use. So I know that a to the nth is going to be equal to that numbered position times that n value plus 1 times that n value plus 2. So when we talk about what are our n values, again, if I wanted to think about it like an XY chart, except for I'm not talking about x's, I'm talking about n's. So here's the first term, the second term, the third term, the fourth term. So what I'm going to do is say, okay, that first term is going to be equal to 1 times 2 times 3, which is going to be equal to 6. Because this one and this one and this one came from this numbered position, and I substituted in for each time I was asked for that n value. My a sub 2 is going to be equal to, here's my 2, here's my 2, here's my 2, so 2 times 3 times 4, which is going to give me 24. All right, so now that you know how it's done, you go ahead and find the third term of this pattern and then the fourth term of this pattern. All right, so when I substituted those n values, which term in the sequence I was talking about, that 3 and that 4 gave me these n values. So here's what this means. My first term in this pattern is 6. My second term in this pattern is 24. My third term in this pattern is 60. And my fourth term is equal to 120. So we need to get used to that n being a representation of our domain or our input, but it's the position of each term. It's the number of term that we have, our first term, second term, third term, fourth term. And that range, that output that comes is a result of whatever rule our pattern gives. So if you saw a list of numbers, let's say you saw 6, 24, 60, and 120, and you knew that there was a rule to fit those, could you get back to this rule? I don't know. That's a little bit of a tricky one. Okay, let's go on to the next page. Okay, so we've seen a couple kinds of sequences, but we're going to talk about specific ones that are arithmetic. And if you have an arithmetic sequence, that means that the difference between any of the two terms is constant. And we're going to call this a common difference, and the variable that we're going to use for it is d. So it goes back to, if you think about where we started, where I had my example where I was adding 1/10, 1/10, 1/10, 1/10 each time. This was a common difference. If you look at number 6, this is not a common difference because I was adding a different term each time. So when we talk about these sequences, we want to make sure that we're looking at each of those n values for the placement of the term and then what happens in between. If you're looking to find the common difference, you're going to subtract. And what you're going to subtract are the two consecutive terms. So if I have my first term, my second term, that second term is the result of your first term plus the difference. Your third term is the difference added on to the second term. Your fourth term is the third plus the difference, and so on and so on. So we get to this important idea too, where each term is equal to that last term plus a difference. And if I want to know what that difference is, all I need to do is subtract two terms to see where did I get from there. If that sounds confusing to you, hold on, because it's much easier in the examples. If you look at this, you take two consecutive terms and you subtract them. 7 minus 4 is equal to 3. Then you check it out and say, hey, wait, is this 3 away? Is this 3 away? Is this 3 away? Because each next term is 3 away, I know that my difference is 3. And I know that that's a positive 3 because my sequence is growing. Check out number 2. When I look here and I see these differences, when I find out the difference between these two, 3 minus 7 is negative 4. So then I want to see, is each next term 4 less? Is negative 1 4 less than 3? Is negative 5 4 less than negative 4? It is, and because this sequence is decreasing and getting smaller, I know that my difference is a negative value. Let's check out number 3. Here I have my plus 1, plus 2, plus 3, plus 4, plus 5. Is it a sequence? Yes. Is it an arithmetic? No, it's not, because there's no common difference. There's no D. That difference is changing each time. So is it predictable? Yes. Is it a pattern of numbers? Sure. But can I use my formulas to determine each next term? Not the formulas we're going to talk about today for sure. All right. Now, we learned our lesson last time with the common denominator, so let's go ahead and put everything into fourths. 4 fourths, 5 fourths, 6 fourths, 7 fourths. Is it a pattern? Yes, it is. Is it arithmetic? I think so, because each time I'm adding 1/4. So my difference here is 1/4. And here's an interesting distinction. Your difference can be positive, your difference can be negative, and your difference can be a fraction. So be on the lookout for each of those instances. Okay, so if you think about the way that we find that difference, mathematicians were able to come up with what they call an explicit rule. And an explicit rule is going to be a formula that you can use to help you find a term based on where it is in the sequence. Which nth term is it? So if you want to find any term in the sequence, we call that a sub n. So whatever term you want to find, we can. So if I have a sub n is equal to a sub 1, and remember a sub 1 is my first term, plus that difference times, and this is an interesting idea because n minus 1 is going to be whatever number term you want minus 1, because that's how many times you've used the difference. So we can go ahead and use this formula to write an explicit rule for each of these sequences that we have. All right. Our first job is to figure out what D is. So for each of these conversations, I would like you to pause the video and you tell me what the common difference in each of these sequences is. All right, so we'll talk about this one first. When I look at this sequence, this list of numbers, I know that in order to get to each new term, I'm subtracting 2. And because that's the same story, it's a common difference. So I know I at least have my D. All right. So what we want to do is we want to write a rule for how this happens. After we write the rule, then we're going to figure out what the 20th term in that sequence is. So first things first, let's write our explicit rule. So we're going to take a peek at our formula and say that any term, whatever your n is equal to, whatever numbered term you're looking for, is going to be your first term. There's that 2, plus that common difference times, and this n minus 1 represents how many times that difference was applied between when you started and the number you want. We don't know our number yet. That's in the second part. So our n is going to stay as a variable. So any numbered term can be found when, and we'll go ahead and do some distributing, and then we'll go ahead and do some combining like terms. So negative 2n plus 4. That becomes our linear rule. And a little secret here, that slope is always going to be your common difference. That's interesting to think about. All right. Now somebody says, well, it's really nice you have a rule, but can you tell me please what my 20th term is? So if I want to know what a sub 20 is equal to, I can say negative 2 times 20 plus 4. So a sub 20 is equal to negative 40 plus 4, which is going to be negative 36. So guess what? That is going to be what the 20th term of this sequence is. And you have to ask yourself if that makes sense. If you're subtracting 20 times on down into the negatives, does it make sense that you would end up down at 36? Negative 36, probably for sure. So there's two ways that you can find that rule. Number one, use your rule and plug in what you know your n is. Our second way is to jump right to this formula and figure out what that next term is. So if I know that a sub 20 is equal to my first term, which is 2, plus my common difference, which is negative 2, and this is where I'm going to multiply 20 times 20 minus 1. So I have a sub 20 is equal to 2 plus negative 2 times, and we're going to call that 19. So my a sub 20 is equal to positive 2 plus negative 38. So my a sub 20 is again equal to 36. So here's the interesting thing that I want you to know is because I was able to simplify this formula, I can go ahead and prove it using my graphing calculator. So when I go ahead and clear the memory, I can go to my function screen and say negative 2n, and we'll use x for any number, plus 4. Now, you and I both know that that's a linear equation with a negative slope and a y-intercept of positive 4. And when we look at the table of values, here's the interesting conversation that I want you to see. See this first term, a sub 1 is 2. A sub 2, 0. A sub 3 is negative 2. A sub 4 is negative 4. A sub 5 is negative 6. So here are my n values. Here's my sequence, and here's what numbered term they are. We were looking for the 20th term, and there it is. All right, let's look at our next example. So we had our fractions, and I hope you follow the hint of putting them into, well, they were already in with common denominators. But you can go ahead and look and see that that difference is 5. So when we go to write an explicit rule for this one, we can say that any a sub n is equal to my first term, which is 1/2, plus my common difference times that n minus 1. And what's interesting is this difference of 5 was applied each time after my initial term, my first term. So here's 1 difference applied, 2 difference applied, 3 difference applied. So my fourth term, the difference was applied 3 times. That's why we have that n minus 1. All right, so any term is equal to 1/2 plus 5n minus 5. So any term is equal to 5n. I'll move my variable up front. And when I add 5 and negative 5 and positive 1/2, I'll get 9 halves. If you do that on the calculator, I don't know if that's right. Let's go ahead and double check that. So I have negative 5 plus 1 divided by 2, 4.5, and then we can do math, frac, and then there's our negative 9 halves. So I was good. All right. If I want to find now my 20th term, I have 2 choices. I can go back and use this formula and plug in 20 for n, or I can use the rule that I've created. So a sub 20 is equal to 5 times that n value minus 9 halves. And again, we can put that right into the calculator. 5 times that n value minus 9 divided by 2, 9 halves. 95.5. So that's going to be our 20th term of that sequence. All right, good job. Let's go on to the next page. So they went ahead and changed it up for us a little bit here. They went ahead and just gave us our difference each time, and they gave us, something other than our first term. So we're going to have to do some sleuthing to figure it out, because I know that, and I'll put my formula up here, any numbered term can be found by having my first term, and that's going to be is it times plus our difference times our n minus 1. Okay, so just like any formula, they like to play with mixing it up and giving you different parts. So here's how this one goes. If I know that a to the 49th is equal to negative 112, check out how I write this. I know that negative 112 is the outcome when my first term is added to my difference times, what was my n in this story? Yeah, 49. So that means that negative 1/12 was the outcome when I started with the first term. And then we can go ahead and simplify this. So 49 minus 1 is 48. And then 48 times negative 3 is negative 144. So then I'm going to go ahead and add my 144 to each side. So when I add negative 112 plus 144, I end up with 32. So what this means is my first term was 32. So when I write the rule, I can say, okay, any term that you need to be found comes from this first term plus that common difference times n minus 1. So I can simplify that. Any term you want is equal to 32 minus 3n plus 4, plus 3. Negative 3 times negative 1 is positive 3. So then we'll go ahead and say that any term that you're looking for is equal to negative 3n plus 35. And you're like, oh wait, I happen to be looking for the 20th term. And you're like, oh, you're in luck, because my 20th term is going to be a sub 20 is going to be equal to negative 3 times my 20 plus 35. So we'll have 20 times negative 3 plus 35. So you say, oh, okay, your 20th term is going to be equal to negative 25. And it's good to check and make sure that makes sense, because your 49th term is more negative than that. So that looks good. You can see my sequence is decreasing. It's going down. All right, let's see if we have more room for this one. We have a difference of 4. Let's take a look at what we have. We have a difference of 4, which means that we're good with this value in our formula. A sub 7 is 16. So 16 is the outcome of my first term plus this difference, which is 4 times, and this n is the story here. An input of 7 gives you an output of 16. So we'll do 7 minus 1 there. So 16 is the outcome of a sub 1 plus 7 minus 1 is 6. 6 times 4 is 24. So my a sub 1 is going to be equal to 16 minus 24, which sounds like negative 8 to me. So that means that my first term is going to be negative 8. When I go to write my rule, I know then that any term can be found when I have my first term plus my difference times n minus 1. A sub n is equal to negative 8 plus 4n minus 4. So a sub n is going to be equal to positive 4n minus 12. So 4 times that, whatever number I have, times 12. So now if somebody says, oh, by the way, can you find the 20th term? You're like, absolutely. All I'm going to do is say my a sub 20 is going to be equal to 4 times 20 minus 12. So my a sub 20 is going to be equal to 80 minus 12. And 80 minus 12 happens to be 68. So what ends up happening for each of these things is you can look at it on a linear scale. You can look at how this sequence goes. And we did an XY chart before, and some folks find it easier to write these horizontally because your N and then your output, or your F of N, is going to be your output. Okay, so the first 5 terms of the sequence, we can go ahead and put in, remember N has to be a real number, so it can't be negative, and it can't be 0. So our first term is going to be a sub 1 is equal to negative 2 times 1 plus 3. So that looks a lot like positive 1 to me. So 1 goes in, 1 comes out. Let's see what happens when 2 goes in. A sub 2 is equal to negative 2 times 2 plus 3. That's negative 4 plus positive 3. Sounds like negative 1. So I know that 2 went in and negative 1 came out. All right, let's take a look at our third term. So a sub 3 is equal to negative 2 times 3 plus 3. So that's negative 6 plus 3, so it's going to be positive 3. So if I go to graph these on the coordinate plane, over 1 up 2, or over 1 up 1, forget that one, not that. Over 2, down 1. Looks like I forgot my negative. Over 3, down 3. I can see the relationship here is linear. And I can see that that change, that common difference of 2 each time in the negative direction gives me my slope. So graphing the points of an arithmetic sequence results in a linear graph, and the common difference is like the slope of the line. All right, so we can use this fact that arithmetic sequences are similar to linear functions. We can find the common difference when we're giving 2 non-consecutive terms. So remember, your M is equal to your slope. So if we write the explicit formula for the nth term, the first thing that we're going to need is that difference. And that difference they're telling us is the slope. So we're going to have to look at how we find that slope here. All right, so let's check this out. If I go from my 10th term to my 3rd term, and then I'm talking about my outcome, I want you to think carefully. When we have slope, remember my slope is my change in y over my change in x. So my change in my terms ends up being in the denominator, and my output, or my y values, are going to be in my numerator. So make sure you follow the same order as when you find the slope. You want to make sure you have second minus first, second minus first. All right, so when I end up with a 14 over 7, I can understand that my common difference is going to be 2. All right, so what do they ask us to do here? They asked us to write an explicit formula for the nth term. That means that instead of doing the math and counting out They want us to come up with a formula rule, a mathematical shortcut. So we can do that, no problem. So I know that any term is going to be equal to my first term plus how many times I've added that difference to it. And I've added that difference by n minus 1. So here's the problem. I don't know my first term. I have my third and my 10th terms. I know my differences too, but I'm going to have to substitute one of them in to be able to find what my first term is. So which one you want to do, a sub 3 or a sub 10? Yeah, I heard you say keep it simple, right? So I know that my third term, here it is, that's 9, is equal to that first term that I'm looking for, I don't know what it is, plus that difference of 2, there it is. And I added those differences together n minus 1 numbers of times. Okay, so 9 is equal to my first term plus 2 times 2. So 9 is equal to my first term plus 4, which means my first term is equal to, subtract 4 from each side, we get 5. Now that I know this first term, I've got this. I figured out this from the slope. So when I write my explicit rule, I can go ahead and say that any term in this sequence, in this list of numbers, is going to be equal to this first term plus this common difference of 2 that's going to be applied n minus 1 times. And I can continue simplifying. I always have to distribute and then simplify. My 2n will move out to the front because it's a variable term. So I have 2n plus 3. If I wanted to figure out what the pattern was here, here it is. I have a slope of 2. And then the first term in my sequence was a 5. All right, let's take a look at this one. The first thing I want to do is find my common difference. So I'll go ahead and apply that slope formula. So I know that negative 47 minus negative 23 is the change in my outcomes. And because I went this minus this, I'll do 11 minus 5, that minus that. So that double negative is going to give us a plus. So don't be embarrassed. Pull out your calculator. You don't want to make any silly mistakes for sure if you can avoid it. Negative 47 plus 23 is negative 24. So that's going to be the output, the change in our output. And 11 minus 5 I know is 6. So I know that my difference is negative 4. Negative 4 is going to be that value. Then I went ahead and did. Okay, so because I had a negative 4, we can go ahead and figure out what that first term is. So we'll go back and get our rule. Any term can be found with the first term, and then how many times did you add that difference? So after my first term, it's going to be an n minus 1. All right, so a sub n, what do I know here? Which one do you want to use? Smaller numbers always. So here's my fifth term in my sequence. My first term, I don't know, but I do know that negative 4 was my difference, and I know that it was applied. Here's 5 minus 1, 4 times. So negative 23 is equal to your first term, and that's going to be minus 20, and then I have plus 4. Or I could have done 5 minus 1 is 4. 4 times negative 4 is 16. So I have negative 23 is equal to my first term minus 16. So my first term is equal to, when I add 16 to each side, that looks like a negative 7. So now that it's time for me to write my rule says, okay, any term is equal to this first term that you just found, plus your difference that we knew from up there, times n minus 1. Any number you just found, negative 7 minus 4n plus 4. So a sub n is equal to negative 4n minus 3. And you can check it out. You can always plug your values in to guarantee that you got the numbers right. All right, how you doing with this? Is your head spinning? You did a good job. 40 minutes is a lot to tune in. I won't put too many Ed puzzle questions in, I promise.